Chapter 12, Section 7, Spherical Geometry. So, pretty much throughout this whole class, we've been learning about Euclidean geometry, which is basically geometry that's in a flat plane or in a space, like your bedroom or your house, right? Like mostly rectangular. It's basic. Everything is basically on rectangles, right? Everything's at right angles, that kind of thing. That it's all based off of. Spherical geometry is different because it's the geometry on a sphere. So instead of working on a flat piece of paper, you're working on a sphere. So you can imagine this like you're working on a globe, which is pretty much what's happening, right? You actually live on a globe right now. It's not exactly a sphere. It's called a spheroid because it's squished a little bit, but you're basically living on a sphere. In terms of most things that we do, they are not big enough to care that the surface you're on is actually curved. When we build a house, we flatten the ground, right? And we can make a pretty flat portion on a very, very small patch of this gigantic Earth that we're on. But when you're doing something like flying a plane from LA to Australia, that covers a good portion of the globe. So you have to start taking care of something called the geometry of the sphere, which is what we're going to be learning about today. Um, the first place we have to start is lines are different. In Euclidean geometry, lines are perfectly straight. Um, that can't be the case on a sphere because the entire sphere is curved, right? So if you look at it from the side, it's going to be like if you look at it straight on, straight up and down, it looks like it's straight. But if you look at it from the side of the Earth, it looks like it's curving around the outside edge. That is technically a straight line in spherical geometry, which might blow your mind a little bit because you can see that it's very much curved. But remember, you're working in geometry of a sphere right now. And just for this section, I'm just going to kind of stretch your brain a little bit out in a different direction. So, um, lines are defined differently. So in Euclidean geometry, the plane P contains line L and a point A not on the line. So basically, the idea is, hey, there's points that make up lines. Awesome, you got points that make up lines, and then there are points that are not on the line. Okay. Um, for spherical geometry, instead of using the word line, we use a great circle. Remember, we learned those in the last section. It's when you cut the sphere with a plane and you get that nice um, uh, biggest circle possible out of the sphere. It's got the same radius as the sphere. That is what a line is in spherical geometry. It's a great circle. So when I drew that little curve there, that's like going from the north to south pole if you were in an airplane. How would you get from the north to south pole? Well, you would just fly straight down, right? But this great circle thing does some interesting stuff. And of course, you can have points not on a great circle. So points can exist outside of a great circle or line in spherical geometry. In example one, just like when you started out with Euclidean geometry, we started identifying lines and points and rays and all the little parts that make up everything. We're going to do the same thing here for spherical geometry. Name each of the following on sphere F. So they don't have it. Well, I guess they do have it down here. You can see it's kind of like an italicized, weird text F in the bottom corner. That's the name of the sphere. Usually it's corresponding to the name of the center. They just didn't want to put it in the center of the picture. But that's where the name is. You can see it's always in a slightly different font. So I want two lines containing point R. Now remember, lines means great circles. Okay, and point R is the same. So let's see if we can find point R. There it is. And you can see I got two lines coming crossing through it. I got one that goes Looks like it goes to point M, and if you follow the other path all the way down, it goes to J. So I would say JM contains R. And then you could also do it in the other direction. Let me pick a brighter color here. From R, you can see it goes to G, and then it swings on down to K. So you could also say GK contains R. All right. I guess since these are lines, we should have little arrows on them to say that they're not infinitely long. They're just a complete great circle, right? If we want a segment containing a point, then we would use similar segment notation. So I'm looking for point K. I'm going to go ahead and erase the last stuff because otherwise my picture gets a little bit too messy here. I'll give you a second in case you want to pause. Okay. Now I'm looking for point K, and I'm looking around. See, there's the bottom there. And I'm looking for a segment that contains point K. Well, there is one that I see right away. Of course, you could have a big one like GK. That is a line segment containing K. I mean, K is in the name. So GK contains K. All right. But that's kind of boring. You don't want it to always be the endpoint. Let's see if we can spot the other one. So I'm going to try to do this in green here. So I got K, and I notice it's on that great circle GK. I can go up and I can get to point P. But if I look on the back side where the lines turn dotted, you can see I end up over on point S. And that one is really hard to see. It's honestly like if you were to draw all of these things on an orange and then rotate it around, it'd be a lot easier to see. And so we'll say also SP contains K because it goes from point S to point P, and it's a segment. It's not going on forever. All right, I'll let you pause that if you want to take a closer look at the picture before I go to the next one. All right. Last one, we're looking for a triangle. Now we know in Euclidean geometry, a triangle has three sides. So I'm looking for three line segments. The problem is the line segments are on great circles now, right? So they're going to be shaped slightly differently. There's actually a ton of different triangles in this picture here, but the one that might be the easiest to see is R. You just got to pick a point there, and it goes down to Q. Q kind of follows the equator over to P, and then R and P get connected there. And there's a triangle in the front. So you could say triangle RQP, or PRQ, however you wanted to put it down. That's not the only triangle out there. There are other ones that are just harder to see. For example, I see S connects up to the Q, over to the P, and then back down to the S. That does not look like a triangle when you're looking at it from that angle, but if we were to pick the sphere up and roll it around, if we were to get that triangle to look right at us, it looked exactly like the triangle PRQ. So that's what gets difficult with these. You don't get to see the whole plane at once because it's a sphere. There's a back side and it curves away from you, so it makes it harder to see everything. But if worse comes to worse, literally grab an orange and a marker and draw on an orange. I might even do that later in this video.